So if you remember, last class we talked about vectors. And the class before that, we talked about constant acceleration motion. So today, we're going to put those two ideas together. And we're going to look at constant acceleration in 2D. All right? And we're going to make it do the sort of the typical example, which is projectile motion near the surface of the Earth. All right, so what does that mean? It means I can write down the acceleration right away. So I have the acceleration A is minus g, and it's in the j hat direction, right? We're going to call j up and down, and x and y elsewhere. So our typical problem is we have some particle that is shot up like that. OK, this is the y direction. That's x. OK? So that's a typical situation. That's called projectile motion. All right? So how do we use that with constant acceleration? Well, we just write down the constant acceleration formulas for each component. All right? So that's very easy. So we write down constant acceleration formulas for each component. So let's write that down. All right? So in the y direction, we have a sub y is equal to minus g. And it's a constant. We have v sub y equals the initial velocity in the y direction minus gt. And y itself is the initial position y plus v0 yt minus 1/2 gt squared. So we're all done. There are three equations in the y direction. And we can also write down the other equation, v sub y squared, v0 y squared, minus 2g y minus y0. So we can write down all of that. In the x direction, we have a sub x is equal to 0. Now we're assuming no air friction. Otherwise, we'd have to change some of this. So that's a sub x. V sub x is equal to v0x plus 0. Because there's no acceleration in the x direction, so the x velocity stays the same. And then we get x itself is x0 plus v0x t. So notice we don't have a t squared term, right? Because the acceleration is 0. Now I can write down this equation, but it's kind of useless because it's the same as this. I just say vx squared equals v0x squared. So that's not very useful. So I have a problem. All I got to do is pick key points and then work out whatever is being asked for. That's all there is to it. It's no different than 1D. It's just more complicated because you have more formulas. All right? So let's do an example to see how this works. All right. Let's find the range. If v0 equals v0x comma v0y. And what do I mean by range? All right, so range equals x minus x0 when y equals 0. Okay? In other words, this is pictorially what it looks like. This is y, this is x, and this distance here is the range. Okay, so that's it. All right, so it's very convenient in most problems to choose y0 and x0 equal to 0. All right, and now I need to find the range. Again, since I'm not interested in time, it looks like these things might be useful. So let's do that. So we have vy squared equals v0y squared minus 2g y minus y0. All right? Now, at this point here, it's very interesting. The final position is the same as the initial. And so we've just shown that vy squared equals v0y squared. We've already learned something. The speed in the y direction here is the same as here. All right? But of course, vy is not equal to plus v0y, it's equal to minus v0y. Right? Because here, v0y, v is positive, it's going up. Here it's going down. Well, that doesn't tell us too much. Looks like we need to get the x range, x0, 0, v0x, it looks like we need t. So we have to figure out what t is. But we've just learned that the final velocity y is the same as this, but negative. So it looks like we can get t right away. All right, so if we look at this point here, that's a very important point, we know that vy equals minus v0y, and y equals 0 there. And just for convenience, we'll write y0 equals 0, x0 equals 0, v0x, we can write as v0 cosine theta, if we write that as theta, and v0y is v0 sine theta. All right, so let's use that time equation over there. So the time equation, so we have vy is equal to minus v0y. That's what we got here. And that's equal to v0y minus gt. And lo and behold, we can solve for t, and we get that t is equal to 2 v0y over g. Very good. All right, so now we know t. We can go back and plug that into x. X equals x0 plus v0x times t, which equals v0x. And t is 2 v0y divided by g. So we get this nice result. 2 v0x, v0y divided by g. And this is equal to the range. Very good. So we computed the range. Now, one thing that's very common is we want to know what's the maximum range you can get for a given magnitude of the initial velocity, v0. What angle should you shoot it at? So what is theta to maximize the range? All right, so I put in for theta what it is. X is equal to 2 v0 squared cosine theta sine theta divided by g. All right, now there are a number of ways of doing it. You could take a derivative with respect to theta, set it equal to 0, and find out what theta should be. Another is to recognize that 2 cosine theta sine theta is equal to the sine of 2 theta. So if you recognize that from trigonometry, then you can look at the answer right away, because you know that the biggest the sine can be is 1. And the sine is 1 when its argument is 90 degrees. So this implies theta equals pi over 2, or 90 degrees for maximum range. So you see that the application of these formulas is very straightforward. Let's see if there's anything else I want to say here. So you can go ahead and do lots of examples. Some of the results you can get are, for instance, the time up is equal to the time down. Right? You could just use those results. And how would you do that? To identify this point is defined by, right up here, Vy is 0. Vx is not 0 there. In fact, Vx never changes. Vx is always constant. It's just equal to the initial velocity. All right? So you can set Vy equals 0 there. You can solve for the time. All right? So if I set Vy equals 0, I get that t is V0 over g. And if you remember, we found before, total time was 2V0y over g. So we've already shown that the time up is equal to the time down. All right? And we also shown that the velocity over here is in magnitude. The speed over here is the same as the speed there, because the x component doesn't change, and the y component just becomes negative what it was initially. Right? More complicated problems would be such where you shoot the object not from the ground, but maybe from a certain height, and then you can follow through. But it's all the same strategy. You start out with the constant acceleration formulas, you draw a picture, you label everything you know on the picture using good notation, and then you have to figure out which of the equations are most useful. So even sometimes when you're not asked for any time, you might need it, like we needed it over here. We had to find the time in order to find the range. If you look at chapter 4, it talks about circular motion and some other forms of motion. We will be doing that a little bit later in the course, so I'm not going to discuss that right now. So right now, our example is projectile motion, and that's what you need to focus on at this point.